nice introduction. This is joint work with Yannick Forster, who's still sitting there in the audience, from Sutherland University. So this work is part of a larger effort to formalize undecidability results in COG. There's already a large library of undecidable problems, for example, halting on Turing machines or Hilbert's 10th problem. And now I'm going to show you how we extend this library with higher order unification. So what is higher order unification? If you've worked in COG or any of the other usual proof assistants, there's a very good chance that you have already encountered it. So if you prove a lemma, such as for all n, n plus 0 equals n, then you can do this with the induction lemma on natural numbers. For this lemma, you need to pick a specific predicate that you want to use for your induction. Now we can pick, in this case, lambda n, n plus 0 equals n. Now, if we do this, we can just apply the lemma and COG will automatically generate cases for us. But it would be quite tedious to always figure out what is the right predicate and then write it down. They can become quite large, for example. So what COG does for you is automatically infer the right predicate in this case. And the process of making this inference is called higher order unification. So if we look at this a little bit more formally, we're given a typed equation between two terms containing constants, which we cannot touch with unification, bound variables, for which the same holds. They cannot be touched by unification. We have three variables which are to be replaced and some typing information on those variables telling us, well, how should we replace them? Now, the solution to this, in this case, is a substitution of P, where we just pick the predicate lambda n, n plus 0 equals n. And then both sides become beta equivalent. So we can reduce the left-hand side and obtain what's written on the right-hand side. Now you might ask, well, I heard of unification, and isn't this decidable? And the answer is, first-order unification is decidable, higher-order unification is not. And to see why this is more complicated, we consider the same case but a different lemma. If we want to prove this now with the induction lemma on positive natural numbers, then this is still possible. But if we ask COG, the proof assistant fails and says, well, I can't unify this. Now, we can still figure out a lemma which works in this case, because we just subtract 1 again from all those positive natural numbers and basically get back our original statement. And here you can see it's not that easy to actually infer the right predicate. So to see that this will still make both sides convertible, you will have to do quite a bit of reduction and unfolding. But it works. So before I tell you the exact proof of why this is undecidable, I want to quickly review what this work is based upon. So in 1973, Huet was, together with Lucchesi, the first person to ever prove a higher order unification problem undecidable. Now, these days, it's commonly attributed to Huet. And he does this by reduction from the post-correspondence problem to third-order unification or anything above that. And then a couple of years later, Goldfarb improved on this result, showing that already second-order unification is undecidable by reducing from Hilbert's 10th problem. Now, around 2000, Dovec came along, gave a nice explanation of Goldfarb's proof, and I'm going to use this explanation today to show you that higher-order unification is undecidable. Now, what we actually did in our work is we mechanized all of these proofs on the left-hand side. We slightly simplified Goldfarb's reduction. We slightly simplified Huet's proof. And we present all of these results in the same calculus. So for example, Goldfarb uses not the lambda calculus, but a calculus with hereditary substitutions, which on the other hand doesn't have binders. Now, what is the calculus that we use that is the same? We use the simply type lambda calculus. So as you can see, we only have simple types. And our basic notion of equality is beta equivalence. As a substitution, we use a capture avoiding substitution, which is automatically derived using the AutoSubs framework. And our typing is Curry style. So as you can see, our binders here are not annotated with any types. For constants, we assume some signature of the types that the constants have. Now, it's actually quite easy to define what higher order unification is. We're given a typed equation between two terms. So here, S and T are both of type A in context gamma. And we ask, well, is there a substitution which unifies both terms? So after applying the substitution, both terms become beta equivalent. Now, this cannot be any old substitution. We want to make sure that the typing constraints in gamma are actually satisfied. So what we do is we require sigma needs to insert well-typed terms, which match the typing constraints for the three variables that are given in gamma. Now, before I show you how to prove this problem undecidable, I want to quickly say what I mean by undecidable. So traditionally, you call a problem undecidable if there's no Turing machine deciding the problem. And you say a reduction from P to Q is just a Turing machine computable function which reduces P to Q. You can switch these out for your favorite model of computation, but basically for your reductions, you always have to reason about the computability. Now, as we just heard, working with Turing machines isn't really that nice, so we took a slightly different approach. We use synthetic undecidability. In the synthetic setting, a problem is undecidable if there's a reduction from a widely known undecidable problem. For example, halting on Turing machines. And a reduction is not a for a reduction, we don't show the computability of some Turing machine construction, but instead, we give a coq function, which by construction is then computable, which still reduces P to Q. Now that we know what undecidability is, we can actually move on to the reduction from Hilbert's 10th problem, what I'll introduce in a minute, what this actually is, to higher order unification. To be a little bit more precise, we don't do this reduction directly. We introduced in the paper an intermediate problem, system unification, which is basically higher order unification, but with a bunch of equations instead of a single one. And it's not that hard to reduce that to higher order unification. But it's also not very interesting, so I'm not going to show it here in this talk. And instead, we're going to focus on this first reduction here. So what is Hilbert's 10th problem? Matyasiewicz, Putnam, Robinson, and Davis, I'm very sorry. All of them together proved that Hilbert's 10th problem is undecidable. That's quite a large effort, and there's now a formalized reduction of this in the library, so we start from this problem. And what it is the satisfiability of Diophantine equations. Diophantine equations are equations over natural numbers involving constants, addition, and multiplication. Now, a solution for such equations is just a mapping from variables to natural numbers, which if we apply it to all the variables and look at the resulting equations, they hold. Now, Hilbert's 10th problem is then, given a system of simple Diophantine equations, does there exist a solution which satisfies every equation in the system? To reduce this to system unification, we're given a system of simple Diophantine equations, and we need to transform them into unification equations, such that the unification equations are unifiable if the original system has a solution, if and only if, sorry. Now, for the reduction function, we use a very standard encoding of natural numbers into the lambda calculus, Church normals. So for Church normals, they represent basically iteration. So if we want to encode the equation x equals 1, we just pick the unification equation where whatever is inserted for x must be equal to the Church normal 1. And for addition and multiplication, we just use the operations that are given on Church normals to encode them as well. Now, this almost works. This breaks if you replace those variables with some arbitrary garbage that contains constants. That might somehow make these equations work, but those are not the solutions you want to think about. So what we, in addition, do is for every variable, we add what we call characteristic equation, which makes sure that whatever this variable is replaced with must be a valid Church encoding and cannot be something with constants in it. And then this basically works. So this is how you can reduce Hilbert-Senf problem to higher order unification. Now, if you take a closer look at this proof, you notice that the terms we used in there are actually third order terms. So you could also make the claim, well, now we've proven that third order unification is undecidable. Unification where all the terms we look at are just third order terms. And as many of you probably know, unification is decidable in the first order case, where there's no interesting reduction going on. This naturally begs the question, well, what about second order unification? And the answer is second order unification, so where we have second order variables and replace them by functions and then beta reduction is involved, is already undecidable. And that's a result due to Goldfarb. I'm going to show you that in a minute, but first I want to make precise what I mean by second order and third order unification. So nth order unification in general is something you can consider as, well, S and T are both of type A in context gamma, but in the nth order fragment. So we restrict everything essentially to order n. And then the solution also has to insert nth order terms and not arbitrary terms. Okay. So before I move on to the undecidability, I want to look at this definition a little, or get a bit of an understanding for this definition. So one result we couldn't find in the literature, but which is actually quite nice because it allows us to show the undecidability of any higher order unification problem by just showing that second order unification is undecidable, is conservativity. Now, for conservativity, this might look very, or to me it looks very intuitive at first, but if you think a little bit about it, it means you have to transform fifth order solutions, fifth order substitutions for second order equations into second order substitutions, which still solve these equations. But this works, we can do this. So we have conservativity, meaning it makes actually sense to prove that second order unification is undecidable and claim then that all other unification problems, higher order unification problems, are undecidable. And we do this now following Goldfarb, where we now need constants G and A of these types. And the reduction is basically the same as the one I've already shown you. But instead of Church numerals, we use what we dub Goldfarb numerals. So where the function that is iterated is fixed to the constant G applied to A. Now, if we do this, basically everything works out except for multiplication. So addition and the characteristic equation, they carry over very nicely. But for multiplication, we have this inherently third order definition for Church numerals. And they don't work anymore with our new representation. So what we do is basically what Goldfarb did. We encode it as this scary looking equation. And in a 17-minute talk, I don't really have the time to get into the details here. But if you're interested in why this is the right way, please have a look in the paper. We dedicated quite some time to find a nice explanation of how and why this works. Instead, I want to quickly recap what our contribution was in the context of the library. So as I mentioned, this already contains a reduction from Turing machines to Hilbert-Senf problem. And we extended this now with the mechanization of Goldfarb's proof, Hilbert-Senf problem, to second order unification. And by conservativity, we get the undecidability of all higher order unification problems. And if you recall our definition of synthetic undecidability, this means we now have proven all of them undecidable. Now, what I didn't get to talk about in this talk so far, and I don't have the time anymore, is that we included also some other stuff in the paper. For example, a decidability proof of first order unification in our calculus. So with beta reduction, but in the first order fragment. And it's essentially the same as first order unification as already known. We simplified Tourette's proof from a reduction from the post-correspondence problem to a reduction from the modified post-correspondence problem. That makes some parts of the reduction a little bit easier. And we took a closer look at constants. So this is second order unification with just the constants G and A in the language. And we can reduce this to second order unification with just G in there, so we can drop the A, giving us an even stronger result, if you will. Just you just don't need this A constant in the language. Now, We also proved that all of these results are, all of these problems are enumerable using standard techniques from the library. In future work, one might tackle the decidability of monadic second-order unification. That is second-order unification where the arity of all constants is restricted to 1. That is actually decidable, but a proof of this has never been mechanized. Yes. And then, in addition, one might want to mechanize the undecidability, Huet's unification procedure, which still forms the underlying algorithm for most unification algorithms today, but its correctness has never been mechanized in a proof assistant. And it's considerably more efficient to enumerate all these problems than the solutions we've presented in the paper. Now, I want to finish this talk with a few remarks on the formalization. So, for example, we use the Brown indices in the formalization, but named syntax on paper to make our constructions more understandable or easier to understand. Normalization shows up all over the place because we frequently do a normal form analysis for our proofs. And usually our terms are typed, so that's not a big deal. We need a constant replacement operation for the conservativity result and also the techniques on constants. And it's straightforward to write that down, but it took a bit of time to figure out the right lemmas to convince Coq that what we're doing in our constant replacement actually works as you would expect. And then lastly, we need quite a lot of meta theory on the simply type lambda calculus, where there's some small details where you would on paper say, well, clearly this lemma holds, but to convince Coq was a little bit more difficult there. Overall, the code is not too much. We use about 3,000 lines of code for just the setup, so unification and the meta theory I just mentioned. And then the actual undecidability proofs are not that big. So the first one I showed you, around 500 lines of code. The second one, 1,000 lines of code. And then there's all the other stuff that I didn't talk about, which takes up the rest. OK, and I will also want to give a shout out to the tools we use. So there's AutoSubst, which we use to generate our substitution operations. That was really nice. We used the equations package to define this first order unification algorithm because it's not structurally recursive. And we use setoid rewriting all over the place because we usually reason quite a lot about beta equivalence. Now, I want to finish this talk by saying this is how we extended the library with higher order unification. If you have any problem where you think this is undecidable, or you know it's undecidable, but its proof has never been mechanized, please get in touch. We're always very happy to collaborate. Thank you.
Okay, this should hopefully be a quick one. So you said that for your reductions, you use Coq functions, which are computable by construction.
Yes.
And well, we know that Coq is consistent under adding a bunch of non-computational axioms. So in this case, that just no longer holds. It's just interpretation of your result, assuming you're working in an axiom-free context.
Yes.
Right? So do you actually sort of translate your reductions into some sort of deeply embedded computation model, like the one from Yannick, or is that?
We have not done this as part of this
But
work.
it would be obvious anyways.
Yeah, also that you've seen a reduction.
Yeah,
so
sure. I've seen the reduction. This is a purely sort of meta question.
Yes. And as far as I know, there's work going on building an actual extraction of Coq functions into.
Okay, I'm aware of that. The question was whether it's used or not.
Okay, it's not used. No.
Okay.
Other questions?
How about matching?
Sorry?
Matching. Like, you have unification, but I think second order matching, for example, is decidable, but higher order, I think, is not, but I'm not sure.
That would also be future work to this.
Right, but have you thought about it or not at all?
Not a lot, no. We are aware, but we, at some point, ran out of time.
So you said that there you followed several proofs from the literature.
Yes.
Were they like apart from the lambda calculus part, were they similar to what you would expect on paper? Or did you like need new ideas to actually formalize or mechanize them?
Well, for example, Red's proof is fairly detailed on paper. What he doesn't talk about are, no, but actually, this is Red's paper for this, and what he doesn't talk about in there is like the small things you need for the lambda calculus to make proofs work at a certain point.
Otherwise, it's basically the same.
Yes.